Somewhere inside OpenAI's infrastructure, a server was quietly dying. No warning, no error log anyone could make sense of. Just a machine that would crash, restart, and act completely normal. Until it did it again, weeks later. When a computer crashes hard, the operating system does something instinctive. It takes a snapshot of everything in memory at the exact moment of death and dumps it to disk. Engineers call this a core dump. Think of it like a chalk outline at a crime scene. The body is gone, but the shape of what happened is frozen there. The problem with core dumps is they are enormous and messy. A single dump can be gigabytes of raw memory, thousands of variables, stack frames, and thread states all jumbled together. Reading one is like being handed the entire contents of a library that just exploded and being asked which book started the fire. For most engineering teams, the standard move is to look at one crash, find something suspicious, fix it, and move on. But OpenAI was seeing crashes that made no sense individually. No single dump told a clean story. The crashes were rare, random seeming, and spread across thousands of machines. So the team flipped the script. Instead of investigating one crash at a time, they started collecting every core dump they could find and analyzing them in bulk. Statistically, like epidemiologists tracking a disease across a population. Here is why that framing matters. A disease that kills one person in a million looks like bad luck. That same disease killing one person per million across a city of 10 million people is a pattern. And patterns have causes you can find and fix. OpenAI operates at a scale where a 1 in a million software event happens multiple times a day. The team built tooling to parse thousands of core dumps automatically, extract structured signals from the chaos, and cluster crashes by similarity. Instead of reading the exploded library by hand, they built a machine that reads every book simultaneously and groups the ones with matching burn patterns. When they ran this across their crash history, two separate clusters emerged. Two distinct shapes of death. That meant at least two different root causes, and at least one of them had been hiding for a very long time. The first cluster pointed to hardware, specifically a subtle fault in certain memory chips that only manifested under very specific thermal and load conditions. The kind of fault that passes every standard test and then fails silently in production. A bad actor that only misbehaves when no one is watching. Hardware faults like this are notoriously hard to catch because the failure is probabilistic. The chip does not always get the wrong answer. It gets the wrong answer maybe once every billion operations. At small scale, you would never notice. At OpenAI's scale, running billions of operations per second across thousands of machines, you hit that threshold regularly. But the second cluster was stranger. It traced back to a bug in a foundational software library. Code that had been written, shipped, and depended upon for 18 years without anyone catching the flaw. How does a bug survive 18 years? The same way a structural crack in a bridge can survive decades. It only matters under a specific combination of load, temperature, and timing that normal traffic never produces. This bug required a precise race condition. Two threads doing exactly the wrong thing at exactly the same nanosecond. A race condition is what happens when two parts of a program try to use the same resource at the same time without coordinating. Imagine two chefs reaching for the same knife simultaneously. Usually one gets there first and no one notices, but occasionally their hands collide, the knife falls, and something goes wrong. The kitchen worked fine for years because the timing never lined up quite right. At normal operating scales, the window for this collision was so small it essentially never opened. But OpenAI's workloads push hardware to extreme concurrency. Dozens of threads hammering shared resources simultaneously, constantly. They effectively widened the kitchen, added more chefs, and suddenly the knife was hitting the floor all the time. Once both root causes were identified, fixes could actually be designed. The hardware issue triggered a replacement and screening process. The software bug, 18 years dormant, got patched, and the fix was contributed back to the open source library so every system depending on it could benefit. What makes this story significant is not just that they found the bugs, it is the method. Core dump epidemiology is a new discipline being forced into existence by the scale of modern AI infrastructure. The problems are too rare, too distributed, and too complex to debug one at a time. It is the same shift medicine made when it stopped treating disease as individual bad luck and started mapping populations. John Snow did not cure cholera by treating patients one at a time. He pinpointed the contaminated pump by plotting where people lived on a map. The insight was systemic, not individual. The limits here are real, though. This approach requires enormous log infrastructure, significant storage, and custom tooling to even be viable. Smaller teams cannot easily replicate it, and statistical clustering will always find patterns. The hard part is telling a meaningful signal from a coincidence, which still requires deep human expertise. There is also a sobering implication here. If a bug can hide in widely used open source code for 18 years and only surface because one organization ran the right workload at the right scale, how many more are waiting? The answer is almost certainly more than anyone is comfortable with. The core dump is one of the oldest diagnostic tools in computing. Decades old, unglamorous, largely ignored. OpenAI's team took that dusty instrument and applied modern data infrastructure to it at a scale it was never designed for. Sometimes the breakthrough is not a new tool, it is using an old one very, very differently.